let's get the Nusselt number, and we can check the correlation of the Nusselt number with the Reynolds number. The Prandtl number is 1 over here, so that term is just 1. And so if we plot the Nusselt number versus the Reynolds number, we can get that exponent and that coefficient, and we can compare the values we get from Fluent to these values from boundary layer theory. And that's a definition of the Nusselt number. H is the surface heat transfer coefficient, and that, so from H we can get the heat flux at the surface or at the plate by multiplying H by TW minus T infinity. And in this case, QW is going to be minus K dt dy at the wall using Fourier's law. And since we now have the temperature variation, this Fluent knows, and K is a constant, so it can calculate QW, and it knows the wall temperature as well as the free stream temperature, so it can calculate H. Now in Fluent, the definition of H is as follows, which is very similar to this, except that it asks you for this input. It doesn't know what the ambient temperature is because it's problem dependent, so it asks you to supply that. And that is done in the reference values panel. So we have to enter this value in the reference values panel, which you interpret as T reference. In our case, that's T infinity, and then use it here, and you essentially get that expression. And then once we get H, we can calculate the Nusselt number. So let's go to Fluent and set the reference values. So you do that under this here, reference values. That's in the setup, and then make sure that that's set to, the temperature reference is set to 400 Kelvin. And then you need to go to run calculation, data file quantities, and make sure H is going to be transferred to the post processor. So it has enough information now to calculate H, but H is not transferred to the post processor by default. So surface heat transfer coefficient, that's H. And we had selected some other quantities previously, which are now deselected. So let me select those. And that's not enough to send it into the post processor. We have to run one iteration. So let me expand this over here and set the number of iterations to 1. And I'll say calculate. And now when I go to CFD post, it'll say new upstream data exists. I'll say yes. Okay, and then if I come into the comment over here, I should see that the surface heat transfer coefficient is one of the variables. Sometimes I have to go and click over here, and you see, oh, it's come in. That's a confirmation. So I want to plot the surface heat transfer coefficient along the plate, and I have to create a line along the plate. So I'll do location line, and I will say, I can't just call it plate because there is, that's a boundary that's come in as a 3D object in CFD post. So I'll call it my plate. And I was playing around with the number of samples. 101 works well. You can get, depending on the number of samples, you can get some funky behavior at the exit. And I think that's because, or at the edge of the plate at x equal to L. And that's because of some interpolation issues. So I'll use 101 samples, and then I can just say chart. So I'm going to plot H versus X. And under data series, I'll pick my plate. Along X, I want X. Along Y, I want surface heat transfer coefficient. And I say apply. And that's H versus X. And then once I have H versus X, right, I can just multiply that by X and divide by K, and that'll give me NUX, and then I can plot NUX versus REX, and REX I can get from X. So let me show you a file where I did this. Okay, and you can replicate that. So I created an expression for NUX, so that's basically HX over K, so that expression. And then I created an REX expression, which is essentially that, and you can see I've given the units, so that's density, kg per meter cubed, and so on. And again, I'll get a non-dimensional variable, and then I created NUX and REX variables from that, and then I plotted it, NUX versus REX, and that plot looks like that. And then I exported that, and I have to, this is a little funky where it goes, so I just went into, I actually did it on my desktop, and I created, you can save it as a CSV file, and once you save it as a CSV file, if you look at that, it gives you, it puts some headers in and gives you REX versus NUX. And so I copied that over to an Excel workbook, and let me bring that up. I call that flat plate calculations. So I copied that data into the Excel workbook. I gave it an appropriate header, and then if I select this data, so I can do that using Control Shift down, and then the right arrow, and then say Insert, and select Scatter Plot, this with smooth lines, and that gives me my plot. I can cut it, sorry, I can, I'd like to have it at the top over here. Okay. And then you see that around, say, 1,000, when the REX value is around 1,000, that's when you begin to get a smooth plot. You get some funky behavior in the needling edge where things break down. And so 1,000 is around, the row 13. So I went in here, I highlighted the curve, I said select data, and then changed that from 3 to 13. Now I get a smooth curve, and then I can say, I can highlight the curve and say add trend line, and we want to power law fit and say display equation on chart. And it shows you what the equation is, and you see the exponent is 0.51, which compares quite well to half, and this coefficient is 0.31, and it's in the right ballpark as this. And there is some finite Reynolds numbers effect, there are some mesh effects. You can also increase the number of samples along your line. All these things will make it, agree better, but that can be quite painstaking. But that's a good, way to at least get into the right ballpark for the polynomial fit. And you can save your project.